In the last lecture, we have seen that a periodic function f of t with time period capital T can be expanded in terms of Fourier series, which is given by this constant a naught by 2 plus summation of cosines and sines with different frequencies, which are actually integer multiples of the fundamental frequency 2 pi by capital T. And we have seen that the constants in this Fourier series a naught, an and bn can be found out by using the orthogonality property of sines and cosines. So a naught is given by this integral over here, and an and bn are given by these integrals. So essentially we take this function, multiply with the corresponding cosine or sine function, and then we integrate over one whole time period, that is minus t by 2 to t by 2. Functions that can be expanded as Fourier series must satisfy certain conditions, and what these conditions are we'll see in a later lecture. But for all practical purposes in experimental science, most of the signals that we measure in any practical experiments satisfy those conditions. So at this point, we need not worry about the conditions that this function satisfies. So for all functions that we will see in any experiment, if they are periodic, then they can be expressed in terms of the Fourier series. So now in this lecture, we look at few examples of Fourier series so that you are familiar with how to compute these coefficients. So let's start with one of the simplest example that I can think of. So let's consider a function f of t equals to sine cube of 2 pi t. So in this case, we see that this function is periodic with time period 1. So let's look at this function. So here is the plot of this function sine cube 2 pi t, and the first thing we see is that this function is an odd function. So what we can expect is that in the Fourier series, which is given by sum of sines and cosines, we should not have any cosine term, because cosine functions are even functions, and here we have a function which is an odd function. So what we'll do is that we are going to find the Fourier series by analyzing this function between time interval minus t by 2 to t by 2. In our case, the function has a time period of 1, so we'll analyze the function between minus 0.5 to 0.5. So this particular function is actually simple, because what I can do is that we can use trigonometric identities to write sine cube 2 pi t in terms of other sines which have different frequencies. So what we'll do is that we'll use the identity sine cube x is equal to 3 by 4 sine x minus 1 by 4 sine 3x. So in our case, we can write f of t as 3 by 4 sine 2 pi t minus 1 by 4 sine 6 pi t. So if I write this function in this form, then all I have to do is to compare the terms with different frequencies on the right hand side of this equation. So we see that for n equals to 1, b1 is equal to 3 by 4, and we have sine 6 pi t term, so we'll have another coefficient which is non-zero, and that corresponds to n equals to 3, so we'll have b3 is equal to minus 1 by 4, and all other coefficients are 0. So, so in this particular case, we didn't have to evaluate these integrals because I can directly look at the coefficients corresponding to sine terms with different frequencies and compare the terms on left and right hand side. But one may ask, that can't I express this function in terms of sines, in terms of sine functions with other frequencies? So the answer is no, because we have this orthogonality property. So if you actually want to use these integrals, what you will see is that if you use this form of the function on the left hand side over here, and then you multiply both sides of this equation by, let's say, sine 2 pi t, then on the right hand side only one term will remain after integration between minus t by 2 to t by 2, because sines and cosine functions are orthogonal with respect to each other. So if we have this coefficient 3 by 4 uh, on the left hand side, that would correspond to b1 on the right hand side and no other coefficient on the right hand side. So this is our first example of Fourier series. So now let's look at more interesting examples of Fourier series. The next example is to consider a square wave with time period t. So let's say we consider this square wave, which is defined by this function f of t. So this wave looks something like this. So the maximum value is 1, and uh, this pattern that it is 0 from minus t by 2 to 0 and 1 from 0 to t by 2 repeats itself after a time period t. So this is how my square wave looks. This square wave can be represented by this function f of t, and this f of t is 0. So if we consider this function between this time interval minus t by 2 to capital T by 2, then I can write it as function f of t, which is 0 for the time interval minus t by 2 to 0, and is equal to 1 over this particular time interval 0 to capital T by 2. So now let's start writing the Fourier series for this square wave. So again, what I want to do is to express this square wave as this series So let's start by looking at the first coefficient a naught. So a naught is given by 2 over t, and integral over this interval minus t by 2 to t by 2 f of t dt. So which in our case our function is has a constant value of 1 in the interval 0 to t by 2, and in the interval minus t by 2 to 0 this function takes on a value of 0. So we can simplify this integral as this, and this gives me a value that is 1. So note that this a naught by 2, a factor of 2 in the denominator in the Fourier series, is just because when we write these equations for the coefficients, all the coefficients a naught, an, and bn have a common factor of 2 by t. So it's just a matter of notation that we have this factor of 2 in the denominator of the time invariant term a naught. So next, let's try to find the coefficients an. So now an is given by integral 2 over t minus t by 2 to t by 2 f of t cosine 2n pi t over t dt. And because our function is non-zero only for the interval 0 to t by 2, this integral simplifies and that function takes on a value of 1 in this interval. So if I solve this integral, I'll get 2 over t, and this integral of cosine will be t over 2 pi n sine of 2 pi n t over t, and I will put in the limits 0 to t by 2. So when I put the limits, we will see that I'll get terms like sine pi n, and another term would be sine of 0, and both of them are 0. So we'll say that this coefficient an is actually 0. So next we can find the coefficients of the sine functions with frequencies that are integer multiple of the fundamental frequency. So coefficients Bn are given by this integral where we multiply our function with sine functions with different frequencies and then integrate over the interval. So if I perform this integration for my square wave, so I will have this integral, and this will be equal to minus 2 over t, because the integral for a sine function is minus of cosine, so that's why we'll have this times t over 2 pi n cosine 2 pi n t over t. And when we put the limits, we'll see that this integral is equal to 1 over n pi 1 minus 1 raised to power n. So this minus 1 raised to power n term comes because when we substitute this capital T by 2 over here, we have terms like cosine pi n, and cosine pi n takes value of minus 1 raised to power n. So for n that is odd, it takes on value of minus 1, and for n even, so cosine of pi n will give a value of plus 1. So therefore the coefficients Bn can be given by 0 when n is even and 2 over n pi when n is odd. Therefore, the Fourier series for the square wave that is shown in this figure over here can be given by f of t equals to, so the time invariant term or the coefficient a naught was 1, so we have a naught by 2, which is equal to half plus summation n goes from 1 to infinity, and we'll just take odd values of n because even values of these coefficients bn are 0. So in this summation we'll just have odd values of n. So we have 2 over n pi sine 2n pi t over t. So this is the Fourier series for this square wave. So one thing that we can see is that this series does not have any cosine terms. So the point is that if I take this signal or the function and subtract this constant term half from this function, so I will get a function like this, and this, the resulting function after subtracting half from f of t, will be an odd function. So that's why we cannot have any cosine terms, so that's why we have only sine terms over here. So now let's see how well does this Fourier series represent this square wave. So what we do is that in practice we'll have to truncate this series because we cannot have infinite summations on a computer. So we'll have to truncate it to some finite number of terms. So what we'll see is that uh, the plot of this function f of t described by this Fourier series for different number of sine terms. So here in this figure, the black line corresponds to my actual square wave, and here I have taken time period of 1. So the wave goes from minus zero point 0.5 to zero point 0.5 and then repeats itself um, with a time period of 1. So in the blue color, we can see the Fourier series representation of this function where I have taken three non-zero sine terms, and we can see that with three terms we are not exactly representing the square wave, but we are kind of approaching the square wave. So with three sine terms, we see that we are not getting exactly the the square wave, but it looks like if we have more number of terms, we'll approach this square wave. So now let's look at what happens if we have five terms. So we see that with five non-zero sine terms in my Fourier series, I get a better representation of my square wave in terms of the Fourier series. Then let's look at 10 terms. So in 10 terms, we see that we go even closer to the actual square wave. And finally, for 40 terms, we have a reasonably good representation of the square wave, except at this sharp edges or the points where the function is discontinuous, where we see this overshoot. The Fourier series in blue color overshoots the value, and there are uh, oscillations, large oscillations, and there are overshoots than the actual value of the function. But away from this discontinuity, this Fourier series is able to get the value of the actual function. We can observe that as we increase the number of terms, the Fourier series represents the general shape of the square wave, except at the corners where the Fourier series overshoots. And this phenomena where the Fourier series overshoots is known as the Gibbs phenomena. The reason for this Gibbs phenomena is that we are trying to represent a discontinuous function. So here we have a discontinuous function, and we are trying to represent this function using a finite number of continuous harmonic functions. So because we are trying to represent this function square wave that is discontinuous at these points, at few points, and we are representing it as sum of continuous functions, and we know that sine functions are continuous, so some of those will also be continuous, and that's why, because we are trying to represent a discontinuous function with continuous functions, we do not get the exact match, and therefore we have these overshoots. So the point is that because sum of continuous functions is also a continuous function, it is not possible to exactly represent the square wave with the Fourier series. So we'll not go into the details of how this Fourier series converges to the exact function in this lecture. We'll discuss it in a later lecture, but you get a general idea that as we increase the number of terms, you have better and better representation of the function, except at the point where we have discontinuity. So now let's look at another example of Fourier series which will give better idea of convergence of the Fourier series. So in this example, we'll consider a triangular wave. So this triangular wave is shown in this plot. So we are representing this wave with the function f of t, and this wave has a time period of capital T. So let's plot this function. So the maximum value that this function has is 1, and this function is represented by these two lines in the interval minus t by 2 to t by 2, and this pattern repeats with the time period t. So we have a triangular wave that looks like this. So we are interested in representing this triangular wave in terms of the Fourier series. So first we'll have to define the function between the time interval minus t by 2 to t by 2 of whose Fourier series we want to write. So this f of t can be written as 2 times the absolute value of t divided by the value of capital T. So at t by 2 we have the value 1, at t equals to 0 the value is 0, and we have this function in terms of the absolute value of time. So this function is an even function. So this function is defined for the time interval minus t by 2 to t by 2. Thereafter the function repeats itself with a period t. So the first thing to note over here is that in this case we have an even function, so we cannot expect that the Fourier series will have sine terms. So in this case the coefficients for the sine terms will be 0. So all we need to do is to find coefficients a0 and an corresponding to the time invariant term and the cosine term. So a0 I can write as 2 over t integral minus t by 2 to capital T by 2, and this integral is of this function f of t, so that is 2 over capital T times the absolute value of time times dt. So because we have the integrand is an even function, so we can write this as 2 times 2 over t, and the integral now goes from 0 to t by 2, and I have 2 t over t capital T dt. So that is, I have 8 over t squared integral 0 to t by 2 and t dt. So this integral is given by this, and this turns out to be 1. So a naught is equal to 1. Next we'll find the coefficients of the cosine terms so an is given by 2 over t and the function times cosine 2n pi t times dt, and again noting that this f of t, so this is my function f of t which is even times another even function, so we have this whole function is an even function, so we can actually integrate over the half interval and multiply that integral with a factor of 2. So now I can write this as 2t over capital T. So you can work out this integral. So I'm skipping some steps. So what you can show is that this integral simplifies to this. So what you will have to do is to do integration by part. This is what I get, 2 divided by n pi squared times minus 1 raised to power n minus 1. So again, in this case, this term minus 1 raised to power n comes from the cosine n pi term after we substitute this lowercase t equals to capital T by 2. So that is, I can write these coefficients an as, so when n is even, you have 0, and when n is odd, you have minus 4 over n pi squared. So these are my coefficients. So to sum up, this triangular wave that is depicted in this figure can be expressed by this Fourier series where the constant term is half, and then I have again summation over n, and we'll have only the odd terms in this summation, so 4 over n pi squared cosine 2n pi t over the time period capital T. So the first thing to note is that in this case of triangular wave, we have coefficients that go as 1 over n squared. And this is in contrast to what we saw for our square wave, where the coefficients go as 1 over n. So this has to do with the fact that a square wave is discontinuous, but the triangular wave is continuous, but its first derivative. So if we take the first derivative of the triangular wave, then the first derivative is discontinuous at these points. So in this case, the function itself is discontinuous at some finite number of points, and in this case, even though the function is continuous, the first derivative is discontinuous. So turns out that for functions that are discontinuous at certain points, the Fourier series coefficients will go as 1 over n, and where we have function which is continuous but its first derivative is discontinuous, we'll have with this 1 over n squared term. Similarly, one can check that if we have a function whose second derivative is discontinuous, but the function itself is continuous and its first derivative is also continuous, in that case we'll have coefficients of the form 1 over n cube. So the point is that if we have coefficients which go as 1 over n squared, then as we add up these terms, then for higher values of n, these coefficients will become smaller and smaller much quickly than what we have for this square wave where the coefficients go as 1 over n. So what we expect is that by taking fewer number of terms, I'll be able to represent this triangular wave much better as opposed to what we have seen for this square wave. So let's see how well this Fourier series can represent this triangular wave. So here in black color we have my original triangular wave, which you can see is although continuous, but its first derivative is discontinuous at these points where you have this sharp edge. So even if I take two non-zero cosine terms in my Fourier series, then we have a pretty good representation of this triangular wave. Now if I increase the number of cosine terms to 5, then this Fourier series shown in blue color approaches the exact function even closer. And if we keep on increasing the terms, at 10 terms, we are pretty close to the exact triangular wave. So one thing to note that even though in this case the Fourier series is looks like it is able to represent the shape almost exactly, but one thing to note is that it's more clear in the case where we have less number of terms, that here at these points the first derivative of this function is discontinuous, but we are trying to represent this triangular wave as sum of cosine terms whose derivatives are also continuous. So sum of continuous functions will be a continuous function. So at the edges we'll never be able to represent these sharp edges with the Fourier series, even though by increasing the number of terms we go pretty close to this edge, but we'll never be able to represent with finite number of terms this sharp edge. So this brings us to the end of this lecture.